here I gave you one. Here I gave you this equation. I have shown you this equation yesterday also. That this is basically the most popular. Again, I'm telling you, it is not the sorry. This is not the only calibration equation. Like I told you that in case of RTD, that whatever is the R naught is equal to RT is equal to R naught 1 plus alpha delta T is very popular calibration equation, but it is linear approximation, and it is you can say that the most primitive kind of RT relationship. There are other models also in the literature, although it is not in your course, so I didn't discuss that. Similarly, this is also most popular one, although it is not the only. If you'll go through the literature, you'll find even better RT characteristic equations relationship. You'll find expressions. You will find. Now I'm coming to here. Beta is a material based constant. Its unit is Kelvin, and you can see the RT relationship means graphical form of this equation is this, and you can see it is highly nonlinear, and means if you are approximating it with the linear um, if you are approximating it with the linear characteristic with the linear line, straight line, you can see here, then the nonlinearity deviation error will be very high. So as I told you that because of the nonlinearity and good sensitivity, because of the good sensitivity rather, it is not used for the larger ranges like this, whatever shown here. It is used for small ranges because it is very sensitive. So we go for we can use it for the detection of small change in the temperature. So suppose we are using it for this small range, then obviously nonlinearity will be less, and if we are approximating it by the straight line, then the error will also be less. So this way, the nonlinearity of the thermistor is basically taken care of, handled rather, you can say. So up to this point, I had already discussed, and um, I told you all these things yesterday. So if anybody is having any query regarding whatever we discussed yesterday and I recapitulated it today, so you can ask, please. Gee, I think I am properly audible to all of you,
Yes, sir.
and my screens are also visible. My
Yes, sir.
slides are also visible. Very few people joined till now. What is the reason? Still trickling in. Anyway, so now I'm going to discuss the next thing about the thermistor. You see, as far as temperature coefficient of resistance is concerned, um, uh, it will remain same for both the sensors, RTD and thermistor, because both of them means as far as definition is concerned, it will remain same, because both of them are the thermal resistive sensors. They convert the temperature into resistance. So you see, as far as your temperature coefficient of resistance is concerned, it is rate of change of means general definition. It is rate of change of resistance or response of the resistive thermal sensor RTD. You can say in here in this case with respect to change in temperature, so to which your thermistor is exposed to. So that's why I differentiated this expression, which is relating the uh, thermistor resistance with the temperature. So we'll get this equation, and as you know that the alpha, that is temperature coefficient of resistance, is basically the fractional change in resistance with change in temperature. So we divided this expression this by RT. So finally we get beta by this expression. So your alpha in this case is equal to minus beta upon t square, and you can see that this minus sign is saying the story that it is having a negative temperature coefficient. You can see that automatically you are getting this negative sign. So this way alpha is equal to minus beta upon t square, where the beta is also in Kelvin and t is also in Kelvin. So if you are anybody is having any query regarding this small derivation, uh, you can ask please. Should we go ahead?
Yes, sir.
जी आगे बढ़ा जाए.
Yes, sir.
Now till now we have discussed this unit is dedicated to sensors, and we started with the strain gauge. That strain gauge is used for measurement of strain, and it is a resistive sensor. Then we discussed RTD. It is a resistive sensor and it is used for measurement of temperature. Then we discussed thermistor. This is again a resistive sensor. So we have discussed three resistive sensors, and all of them are passive sensors. Now I'm coming to thermocouple. Can anybody tell me about thermocouple? Here we are not talking about the sensor or something like that. I'm just talking about the thermocouple. So anybody is having any knowledge about the thermocouple? Let me know whatever you know about thermocouple. Thermocouple is a one thing, and thermocouple here we will discuss the thermocouple as a sensor. Thermocouple is having many applications, but here in this unit, in this class, in this subject course, we'll discuss thermocouple as a temperature sensor. So if anybody is having any knowledge about the thermocouple, then please let me know. Yes, please. Somewhere in physics, I think you must have studied. Nobody knows or nobody is interested in sharing. Anyway, thermocouple, as name suggests, it is basically um, a couple. Couple means it comprises two dissimilar metals. Two dissimilar metals. It is made up of two wires of different metals, and they join together. Obviously, when you will join two wires, then you will have two junctions. Here you can see this is one junction. This is another junction. Few thing I'll tell you about the thermocouple when it is used as a temperature sensor. You try to means keep in your mind these things, salient points that I'm going to tell you. They are very important, and if you are having a knowledge of it, then there are two things. One thing is that you can use whenever in the field when you are using it, then you'll have a full knowledge of it. Secondly, in your competitive exams and interviews also many questions are asked. So if you are aware of the fundamentals, then you'll be capable of giving the answer fundamental, because most of the question are based upon the fundamentals. So please try to be attentive. So here right now I'm not talking about the thermocouple as a sensor, I'm just talking about the thermocouple. So here you can see that this is having a two junctions, and when these two junctions are maintained, so this is made up of dissimilar metal, one thing. Two wires of different metals are taken, and then they are joined together physically. Your thermocouple is ready. Now there is a certain condition under which it works. So when these two junctions, resultant junctions, are maintained at different temperature. Obviously, one of them, if we are talking about the different temperatures, so one of them will be at the higher temperature, other will be a lower temperature. So whatever junction which is maintained at the higher temperature, it is in general nomenclature, it is called hot junction, and whatever it at the lower temperature, it is called cold junction. So when this is done, then there will be the polarization of charges. Your charges from the means especially electrons will get the energy at the hot junction, and they will move towards the cold junction, and because of this polarization, there will be the generation of the voltage. And this voltage, whatever voltage that is generated, obviously depends upon two things. One thing is the metals, different metals are used. What are the different metal which are used? And second thing, how much temperature difference has been maintained. So this is how thermocouple works. Now, so when we maintain the junctions into a temperature difference between the junctions, then a voltage is generated. So obviously this voltage depends upon two things. That's what I told you, that the metals which you are using. Obviously, for same temperature, if you are using different metals, you'll get different voltages. One thing. Second thing is the temperature difference. How much? With more temperature difference, more voltage. Less temperature difference, less voltage. So this is how the thermocouple works, and this particular working is basically described by Seebeck effect. You see, Seebeck effect. You must have studied in your physics class earlier. Seebeck effect is summarized basically whatever I told you about the working. That is basically Seebeck effect, and this is summarized in this equation. So E is equal to integration, temperature integration of QA and minus QB, where QA and QB are basically the thermal transport constant of two metals, metal A and metal B. And T1 and T2 basically are the temperature of your junctions. So in this case, if you look closely, you'll find that this generated voltage will be zero if you are using same metal, if you are using same metals, because QA minus QA will become zero, so you won't get any potential. Or if your junction are maintained at the same temperature, T1 is equal to T2. Obviously, in that case also, although you are taking two different metals, QA and QB, but the junction resulting junctions are not maintained at the same temperature, at the different temperature, but they are maintained at the same temperature. Then T1 minus T2 will be zero. Again, your potential will be zero. So the condition for the generation of voltage through this setup is known as Seebeck effect, that you have to maintain it at you have to take the two different metal wires, and then the resultant junction should be maintained at different temperature. Only then voltage, you will get the voltage output. And obviously this voltage depends upon the metals used and the temperature difference. Now I'm coming to the thermocouple as a temperature sensor. This is whatever I discussed till now about thermocouple. It is thermocouple as a thermocouple. Now I'll come high. How can we use this setup for the temperature sensing? Can anybody tell me, having any idea about this? The thermocouple, application of thermocouple as a temperature sensor. G. It is not like testing of your knowledge. It is not like testing of your knowledge. It is about only the, if you know. Yes, somebody was speaking something. Anyway, now thermocouple is a, unlike your whatever sensor, resistive sensor we have discussed till now. Unlike that, thermocouple is a basically active sensor. Here you see, we are not connecting any source to it. It is self-generating type. In response to the temperature difference in a setup, voltage is generated out of blue. So this kind of sensor are called active sensor, unlike your resistive sensor that we have discussed till now. Over there, if you want to convert the resistance change into the voltage, you require a supply and a circuit. Here, that kind of thing is not required. You see, it's okay to all of you. This is an important point. That's why I'm emphasizing on it. This is a active sensor. Example of active sensor. In this case, your response is voltage, and obviously this is proportional to the temperature difference. Now, third point is very important. When we are using it as a thermocouple is used as a temperature sensor, then here in general, as I told you earlier also, in general, it is called, its junctions are called hot and cold. Means because temperature difference is there, so obviously one of the junction will be higher temperature in comparison to other. So whatever is at the higher temperature, it is called hot junction, another is called cold junction. But when we are using it as a thermocouple, then nomenclature and significance, both of them is different. So one of the junction is called measurement junction, and this junction is exposed to the temperature which we are interested in finding, which we are interested in measuring. So one is called, suppose this is the junction which we are terming as the measurement junction. So this junction will be exposed to the environment whose temperature we are interested in finding out. So it will expose to that ambience whose temperature we are interested in finding. And the another junction in this case is, it is called reference junction. It is called reference junction. So this is your called measurement junction. This is called reference junction. Where reference junction requirement, when we are using it as a temperature sensor or a thermal sensor, then requirement for the reference junction is that its temperature should be maintained at constant value. Constant value. Here this temperature is unknown, which we are trying to measure with this sensor. Okay. And as far as your reference junction is concerned, it is maintained at a constant temperature. And this is good if this constant temperature if it is 0 degrees Celsius. 0 degrees Celsius. It is constant. The reference junction temperature should be constant. This is essential requirement. And at what value it should be constant? If it is 0, then it is a desirable situation, desirable requirement. And if it is maintained at 0 degrees Celsius or at some higher temperature, that temperature, your reference junction temperature, should be accurately known. So I have given you the different condition. One, I'm revising whatever I spoke about it. I'm revising again, repeating it, and you try to listen it carefully and try to remember it. Keep in your mind. So these all are very important. So when we are using thermocouple as a temperature sensor, then one of the junction is called measurement junction, and this junction is basically exposed to the temperature which we are interested in measuring. Second junction, another junction is called reference junction. This junction is maintained at constant temperature. This is absolute requirement. And this particular junction, if it is maintained at 0 degrees Celsius, so it is a desirable thing. It is a good that it is maintained at 0 degree. But if it is not, it is not always possible to maintain the reference junction at a 0 degree Celsius. If it is not possible, then you can maintain it at some other higher or lower temperature as per your convenience, but it should be constant. It must be constant rather. Okay, so this is what is the requirement. So that's what it is written all here. This is about the two junctions. Then this is about the reference junction. The temperature of the reference junction must be accurately known. At whatever temperature your reference junction is maintained, it should be accurately known. Then another thing, reference junction must be maintained at a constant temperature. It is better if the reference junction is maintained at 0, but it is not. So that's what I told you earlier. Now, generated voltage is obviously proportional to temperature difference. So this is your measurement temperature and this is your reference temperature. and obviously your reference temperature is constant. So your voltage is, and measurement junction, it may be constant, it may be variable. So measurement junction will be always proportional to T measurement. So it is having a linear relation, linear kind of relation, you can say. So this is how thermocouple is used as a temperature sensor. If anybody, whatever I spoke about the thermocouple and thermocouple as a temperature sensor, if anybody is having any query, or since earlier wherever you may have studied, and if you are having any query because of your concepts, you can ask, please. जी बताइए.
Excuse me, sir.
जी बोलिए बोलिए.
Sir, as we are giving heat source to the measuring junction, सर हम लोग जो मेजरिंग जंक्शन में हीट सोर्स दे रहे हैं,
जी जी,
तो कंडक्शन की वजह से सर कोल्ड जंक्शन जो वहाँ पे भी तो जाएगी हीट, तो सर वो डिफरेंस आ जाएगी ना, कांस्टेंट तो रहेगी नहीं.
क्या डिफरेंस आ जाएगा?
सर जंक्शन का जो टेम्परेचर है, कोल्ड रेफरेंस जंक्शन का जो टेम्परेचर है, वो उसमें तो डिफरेंस आ जाएगी ना, वो तो कांस्टेंट रहेगी नहीं तब.
क्या डिफरेंस आ जाएगा?
सर जैसे कि हम लोग मेजरिंग जंक्शन में हम लोग हीट सोर्स दे रहे हैं, तो ड्यू टू कंडक्शन इट विल ट्रेवल टू जंक्शन, कोल्ड जंक्शन हो ना.
नहीं, देखो, आपको आपका जो रियल सेटअप होता है, इट इज नॉट लाइक दैट कि ये 1 इंच की दूरी पे होता है ना. दे आर एट larger distances, like your measurement junction will be at the shop floor. It is connected somewhere in the processes where processes are going on, and your cold junction is maintained at a means your control room, and it is put in the, suppose if you want to maintain it at 0 degrees Celsius, then it is put in a ice bath, ice bath. So it is your responsibility that you should keep on maintaining it at 0 degrees Celsius in the control room, wherever it is. You understanding what I'm saying?
Yes, sir.
So situation is not like that. It is your responsibility. If you want to use a thermocouple, then you have to maintain the temperature of the reference junction at certain constant value. And if this constant value is 0 degrees Celsius, then it is, so only then your thermocouple will work. Otherwise, it won't work. Like you are exposing this whole hot your measurement junction to certain temperature, and whole thermocouple is then maintained at the same temperature, then it is not going to work at all. So it is not like that. It will work on your whims and fancy. It will work as per the Seebeck effect. So if you will satisfy the Seebeck effect, only then you will be able to use it. You got the point?
Yes, sir. Thank you.
Any other question? Now, different metals, which is very popular and commercially available. So different type of thermocouples are available in the market, and they are identified by their type, not by the metals. So B type, E type, J type, K type, N type, and they are standard. I'm telling you, they are standard thermocouples. If you purchase from anywhere in the world, you will get same kind of characteristic. Same kind of characteristic I'm talking about. So B type is made up of, you can see the material and composition, all these things. Iron consistent, nickel, chromium, nickel, aluminum. Many metals are used, and these are the commercially available standard thermocouples, and their temperature range because of the characteristic of their metal used, and you can see that they are used at different temperatures. But if you go to the market, then you have to specify which type of thermocouple you want to purchase: B type, E type, J type, K type, N type. And then if next important thing, I'm coming to that, is calibration. Here you see, in this case, in thermocouple, what we are doing, the thermocouple is doing, this is converting the temperature into the voltage. Now we require a relation like any other sensor. Now we require a relation between temperature and voltage. So in this case, there is no mathematical relation. Instead of that, we have discrete table. like this. This is called, I downloaded it from the internet. This is, you see, the thermocouple calibration table for type T thermocouple, for type T, copper constant. So here, the copper constant. Constant is basically alloy of copper and nickel. Now this is very important. If you cannot read it properly, you cannot measure the temperature with the thermocouple. So in this case you will find there is no response and stimulus characteristic, characteristic equation, but it is available in tabular form. Now if you look upon the table, please look it carefully. At the top there is the here at the first column there is a temperature in Fahrenheit. You see here 150. Then this is, and then all other columns are the voltages except the last one. So this means if your measurement junction is maintained at 150 Fahrenheit, and all these tables, they are standard tables for a type of thermocouple, and in this case your reference junction is maintained at 0 degrees Celsius. It is maintained at 0 degrees Celsius, and that's why it is always desirable, because all the standard calibration tables are means the data is the data points or measurement is done. They are available for 0 degrees reference junction temperature, and that's why it is always desirable that we maintain our reference junction at 0 degrees Celsius. But many times it is not possible, especially when you are working in the field. It is not possible to maintain the reference junction at 0 degrees Celsius. Then what is done, we'll come to that. That is also a pertinent issue. But here we are concentrating. So in this case, you see that if your measurement junction is at 150 and your cold junction, reference junction is at 0 degrees Celsius, then output voltage will be 2.712 millivolts. You see, it is given in the millivolt. And then if it is maintained at 151 degree Fahrenheit, then it will give you this T-type thermocouple will give this voltage, and so on. So the method is will be reversed. When you are using it, then you will get using a thermocouple. You are exposing a measurement junction to certain temperature. You are maintaining your reference junction to a 0 degrees Celsius, and then certain voltage will be generated. Suppose if this voltage is 2.761 millivolt, then we'll say that the measurement junction is basically the volt temperature to which your measurement junction is exposed at 152 degree Fahrenheit. So this is what is. So here I try to explain. I have written all those points which I spoke. In standard thermocouple table, reference junction is maintained at 0 degrees Celsius. That's what I told. The standard thermocouple table is used to find the temperature of the measurement junction against the generated thermo EMF for given reference junction temperature. Typical thermocouple table reading. Whatever I try to read in the table, that I given in a very easier form. So your measurement junction is maintained at 210 degrees Celsius. The output voltage is 11.34 millivolt. It is from the table only. Type J, your thermocouple is type J, and reference junction is maintained at 0 degrees. This information is extracted from your table. Similarly, other way around, your voltage, if your voltage output voltage is 4.768 millivolt of a type S thermocouple, then temperature corresponding to it is 555 degrees Celsius, and obviously your reference junction is. So these informations are extracted both ways. If you know the temperature, you can find out the voltage for a particular type of thermocouple. Obviously, if you are reading the table, so reference junction is always at 0 degrees Celsius. It is the requirement. And other way around, if you know the thermocouple output, then you can find out the temperature from the table for given and for given type of thermocouple and for given temperature. And obviously, your reference junction should be at 0 degrees Celsius. So if anybody is having any query regarding thermocouple table we discussed till now, it is very important thing, I'm telling you. So you can ask it, please. Everything is in front of you. If you are having any confusion, आपको थर्मोकपल का रीडिंग देखना है, उसके बाद आपको यहाँ से टेम्परेचर मालूम हो जाएगा. So this is the table and this is how we read it.
सर.
ठीक है, आगे चले
सर.
हाँ, बोलिए बोलिए.
Sir, in the table, the reference value will always be 0 degree.
हाँ, we require it. This is the requirement. अब आप ये पूछ सकते हैं कि अगर 0 पे नहीं होगा तो क्या करेंगे?
Yes, sir.
है ना? This is the obvious question. तो ये अभी आपको थोड़ा सा नहीं, टीवी का सीरियल देखते हैं ना, तो एडवर्टीजमेंट के बाद, तो ब्रेक के बाद मिलेगा. तो अभी हम विल कम टू दैट पॉइंट, है ना? लेटर ऑन विल कम टू. लेकिन अभी जो चीजें डिस्कस की है उसमें कोई चीज ऐसी है जो आपको नहीं समझ में आई, you keep aside that query. We'll address that.
Okay, sir.
अच्छा, एक क्वेश्चन तो आ ही सकता है कि भाई जो कोई डिजिटल सिस्टम तो है नहीं आपका थर्मोकपल, तो आपका जो वैल्यू आ सकती है, और टेम्परेचर भी कोई जरूरी नहीं कि 150 के बाद 151 ही हो, 152 ही हो, 153 ही हो. समझ रहे हैं बात की नहीं समझ रहे? तो और ये वैल्यूज भी कोई जरूरी नहीं कि यही हो, ऑल्दो इट इज वेरी फाइन, इंटरवल इज वेरी स्मॉल, बट sometime you may find the reading in between, है ना, in between consecutive readings, and your temperature may also be in between 151 and 152. 1 degree Fahrenheit differences, but your temperature may be in between also. So obviously in those cases you will get the voltages in between. So for that we require interpolation. Interpolation is used. Means if you are having a temperature between these two, temperature and these two voltage reading, then we go for the we assume that the for this interval the characteristic is linear. The linear interpolation is done. So for that, this is the equation, interpolation equation, y is equal to mx plus c kind of equation. So you can see that if you know the voltage, this is your measurement voltage, and this measurement voltage is lying between a higher voltage and a lower voltage, then we will interpolate it, linear interpolation. So your measurement, the corresponding value of that temperature will be equal to the lower temperature from the table. This is your reading. This is your reading, whatever you are getting from the thermocouple. Then you will match it in the table, and you will get it is not perfectly matching with any value. Then we will take the two consecutive readings in between, where in between those two reading this reading is falling. Then we'll note down the higher value and the lower value of this to this value and corresponding temperatures, and then we'll feed all these things and we'll get the output. And vice versa, if you know the temperature and you wish to know the voltage, corresponding voltage from a table, then also you have to do this kind of. So both of them are contemporary. Only thing is that in first case y is temperature, in other case y is your voltage. So if anybody is having anything, any question regarding this, you can ask, please. Now after that we'll discuss empirical laws. So empirical laws, basically I want to discuss in one go and its significance. So I'm closing my today's discussion here only. So if anybody is having any question about thermocouple, whatever we have discussed till now, the most important part of thermocouple that I have discussed is the condition for thermocouple to be used as a temperature sensor, measurement junction, reference junction, their requirement, all these things. Second part is different type of thermocouples. Third part is this calibration. This is treated as calibration table, and this is a standard in this is available nowadays online. You can find out for any type of sensor, thermocouple, you can find out the table. And tables, what is table requirement, and how can we read the table, and how can we interpolate the table. All these things are absolutely necessary. This knowledge is absolutely necessary if you are using thermocouple as a temperature sensor. So the interesting part, another question, whatever someone has raised, that if we are not able to maintain the reference junction at 0 degrees Celsius, then what should we do? That we that query is that is a pertinent issue, and this query is addressed only after knowing these laws. So there are the 4 or 5 laws. We'll discuss it. They are very interesting, and then every law is having its own significance for the use of the thermocouple as a temperature sensor. So we'll discuss all these things. Okay. So I'm closing my today's discussion here. If anybody is having any query, you can ask. Otherwise, I'll take your attendance and we'll move on. Anyway, you respond your roll call.